Okay, welcome to a new video. This one's gonna be very different. We're just gonna learn, and we're gonna see how I try to understand things. So it's gonna be longer. It's not gonna be short. Today we're gonna try and understand flex attention. I've heard this term like literally thousands of times, and I think it's finally time for us to understand what is going on. So let's recap my understanding. So the basic idea is that flex or attention mechanisms, there's a variety of ways to do attention. So there's no bias, alibi, self-cap, etc. And basically in the past, people would come up with kernels, like flash attention and stuff like that, but it's not very flexible. And like the whole point of flex attention is that it covers everything. And the way it covers everything is it uses torch compile under the hood, so that it compiles custom kernels. And then if we think about what attention actually is, it's just this like QKV calculation. And so the insight is that flex attention allows you to apply the score mod after the QK matmul. And then this function in itself allows you to express a lot of different attentions. And then furthermore, one thing you'll notice about attention is that it's kind of sparse. So like if you look at the vanilla attention, you oftentimes have these like dual triangles, right? Where you only care about the computation here because of the causality moving forward. So like, it's like if you have two words, you shouldn't peek at the next word to guess what the next word is. And so you have this like weird thing where as your sequence length increases, you get this like triangle pattern. Okay. All right. So and then with attention, especially with these like multimodal models, there's also this idea of like document attention. So for example, in your context window, maybe you have like 3 different Google Docs or something like that. And then so you don't want like one doc attending to a different doc. Okay, so then you have these patterns like this. Oh, sorry, going back. So the reason why this is important is because if you think about it in terms of computation, it's really inefficient to compute attention for these sparse parts. Like we know they're 0. So anyways, so flex attention, I think it's really, there's really 2 main complexities. There's the score mod, which is what we talked about, which basically allows you to express different forms of attention. And then there's mask mod. And what mask mod allows you to do is express the flex attention. What are the blocks within the attention matrix that we just don't care about? And then torch compile can under the hood like do things to skip those. Okay, so I think at a high level that's how it works. So what I did was I asked Claude, here, maybe let's do this. So I asked Claude to write me a flex attention file. So it's here. So let's take a look. All right, so why don't we just take a look through this? So flex attention has these imports. As you can see here, there's this like create block mask, create mask. There's also a way to compose masks together. You can and mask or mask. There's a nope mask, which maybe is like the sentinel mask. I don't know, we'll see. Block mask and aux request, okay. Can I use? Oh, that's good. Okay. Good. Okay. So let's see. So we construct the query key value things here. We do torch compile flex attention, which is interesting. So I guess flex attention is just a function that you can torch compile. Basic usage. basic flex attention, compiled flex query key value. Okay, so this is nice. So basically, I guess the very basic contract of flex attention is you can literally give it QKV and then it'll give you an out. Also, I have this thing here. So why don't we just like write down questions as we go through them? So one question is like numerics. So like, does flash attention and flex attention have same numerics? I'm guessing because we're using like Triton under the hood that the reduction orders might not be guaranteed to be the same. So I would guess no, but we can figure that out as we go. Okay, so score mods. So this is where flex attention presumably should shine. So as you see, you call flex with QKV, and then you give it a causal score mod. And QIDX. Interesting. So this is, I think this is how it's doing this causal masking thing. Where it's basically saying if the query index is greater than the key index, then just set it to -infinity. And then that gives you your causal. Relative position bias. I see. And then so this is like some like bias thing you can do where you add the distance between Q and K to the scores. Okay. All right, this is not that interesting. Let's talk about other things. So captured buffer per head temperature scaling. Okay, so this is I guess this is kind of interesting. So here we can see we're passing in this temperature scaling score mod. And then this temperature scaling score mod is capturing this buffer. And how does this work? This works because under the hood, flex attention is using torch.compile. And torch.compile is arranging the bytecode to basically get this value. Okay, so why don't we, so I generated a TL parse. It's a little bit hard to know. How can I tell? Maybe let's just do, does that work? I think it's because, yeah. Well, I guess another thing we could do is we could just delete it. All right, let's just delete it. Let's just delete it for now and regenerate the TL parse. Okay, so what I want to show is the Dynamo bytecode that is doing this head temperatures thing. Unfortunately, Dynamo bytecode is really, really hard to understand, and it doesn't show in TL parses, so we might not be able to see everything. But hopefully we can at least see the Dynamo graph and see how this head temperatures. I suspect this is being hoisted as an input. That's my guess. Yeah. So you can see here this G import main head temperatures thing. And this is Dynamo arranging the bytecode so that every time you run this compiled flex thing, it has bytecode to basically have this as a graph input. Okay. It's quite interesting actually. And then it's interesting because this is, okay, let's see actually. So what is G had okay. Yeah, so the thing I was confused about is like, how is it that we can express this indexing? And I think the answer is flex attention does this higher order op. And this higher order op has a score mod, which does, so okay, yeah, so basically this corresponds with this, and then this corresponds with the division. So that's score mod. Where did the mask function come from? Maybe that's like an implicit mask function. Or maybe like mask functions by default, you just always have one and it doesn't do anything unless you provide one. That's probably what's happening. All right, good. Let's keep on going. Okay, I think this is just more demonstrations. Okay, block masks. So causal mask. Create block mask, causal mask. Yeah, so this is so right. So one way you can express this is via score mod that makes all of these negative infinity. But another way is to do this masking, where we say, oh, like, you know, if the query IDX is greater than or equal to the key IDX, just like mask it out. That's interesting. Okay, so taking a step back, like, intuitively, a score mod seems very simple from a torch compile point of view. Like, a score mod, you're basically like pointwise fusing these operations. I think what I'm more curious about is these block masks. Okay, let's see how these block masks work. So what I expect to see before we look at the code is the mask function. I expect to be causal. Like I expect this thing to be encoded in this thing. But let's see. And then what are we going to do afterwards? So once we verify this, I think what we should do is we should go through the code and we should figure out the Triton kernels that are being generated for this. Okay, perfect. So as you can see here, this QIDX KVIDX is encoded here. And of course the score mod is doing nothing in this case. Okay. So now what I want to understand is as we go through the graph, what happens? So for those who are unfamiliar, and it's definitely not something I know very well, my general understanding of a higher order op is basically like a black box. And what you're doing is you're crossing your fingers and hoping that sometime in the future, it's going to go away. And it's either going to go away via decomposition or it's going to go away via lowering, but it's going to go away at some point in the compiler stack. So right now, from the standpoint of this like compiler graph, we are just going to treat this flex attention as this black box that's going to take in all of these things. So I suppose the question is, where does it go away? And I think it goes away in inductor And the way that we're going to figure that out is by looking at this after joint graph. Yeah, so you can see after the joint graph, we still have this flex attention hop. We see that, I think this got lowered to A10, which is fine. And then what I expect to see is, yeah, so it's still here. And then the inductor output code is where it goes away. Okay, so let's see what's happening. So the call does all this. Triton temp fuse flex attention. QKV. Where's mask mod? Wow, that's really interesting. Okay, that's really interesting. Okay. So, this requires a little bit of Triton background. And I'm no Triton expert, but I think this is how it works. So, the way Triton works is you write these programs. This is a Triton kernel. And the basic idea is that, you know, when you execute a program on a GPU, you actually have like tons and tons of parallel computation going at the same time. And the way that we represent this computation is through these program IDs. And the basic idea is, let's say you have like, you're doing a matmul, okay? And you somehow have like, you've expressed, you've expressed the matmul in terms of a series of parallel things, like maybe you tile the matmul or something like that. The basic idea is that if you have like, let's say you have 10,000 programs, then you're gonna have 10,000 different program IDs. To be honest, I'm not like super clear on this, but the basic idea is that this code is gonna be invoked like 10,000 times. And then this will be different based on the tile that you're processing. And so my understanding of what's going on here is that this Q start represents presumably the index of Q that you're starting from. And then flex attention is using this Q start offset to calculate the block mask. And you can see that here. Like the Q offset becomes offset M, and then offset M, you get this index M, and the index M you can use for your mask, and then the masks get used in this tl.store. Okay, I think this makes sense. So is that it? Is there more stuff? Sliding window, custom block size, mask composition. Okay, I guess one thing I also want to show is I want to find a good. Okay, I wanted to find a score mod that is not just the identity function. And for this one, if we look at the inductor output code, negative inf. I hope they're not doing something smart with optimization. I think what's confusing to me here is that this add is an F16. So why are we... I feel like I don't understand the score mod stuff. Let's do a basic score mod stuff. Score mod. Okay, what do we do here? We're just, instead of setting it to negative infinity, we'll set it to 1, 2, 3. That's interesting. It doesn't support broadcasting. All right. Okay, that took a long time, but hopefully you're seeing what I'm seeing, which is basically the score mod gets lowered into this, right? So like when we do score 104561, blah 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 blah, you see it like corresponds with this. Okay. Okay, I think I understand most of it now. Why don't we I think I understand most of it now, actually. Okay, I might just stop here. Why don't we just do a quick recap, okay? So FlexAttention is this like fancy thing that allows us to express attention as basically score mod, but there's this like block mask thing that is useful for efficiency. At a high level, FlexAttention under the hood uses torch.compile. And what torch.compile does is it uses a higher order op to represent FlexAttention both as a score mod, but also as a mask mod. And what happens is FlexAttention is a hop, and it basically is just flows through the compiler until it gets to inductor. So before inductor, it's just treated as this like opaque thing. And then once you get to inductor, then you generate the kernel. And the kernel is basically just like the single FlexAttention kernel. Well, actually, is that true? I guess it's like more, this is so interesting. Okay, well, for block MN. Well, yeah, okay. Anyways, I think it's a single kernel. I think there's a contract for one FlexAttention kernel. Anyways, this score mod gets basically lowered into this Triton code. And then the mask mod, which I don't have here anymore. Where is the mask mod? Do I have a mask mod? Ugh, I don't have it anymore. Yeah, I don't have it anymore. Anyways, you saw earlier, like it's the mask mod is used is also used in the kernel to mask things. Oh, now I'm confused. Oh my god, I wish I could go back. Whoops, I deleted it. part of. Yeah, so the mask was not obvious to me. We should look at the mask. No, I mean the whole file. Like, how does the mask... The fuck? Why is how is this data dependent control flow? What in the world? Why is... Why? I think I was wrong earlier. I think the block mask was actually applied here. I think what I was saying was wrong earlier. Yeah, it's like here. Okay. All right, this is good. Okay, we're gonna summarize one last time. So this is actually kind of interesting. So yeah, at a high level, FlexAttention is really just a score mod and mask mod, and both of these end up happening just within this little bit of code. And then under the hood, torch.compile is basically taking that user Python API, capturing it as a graph where there's a hop in the graph. And then as it goes through the torch.compile stack, that hop just stays there until we get to inductor, and then inductor generates the kernel. And when it generates the kernel, it takes those two score mod and mask mods and basically lowers it to Triton. Yeah, that's kind of how it works. Hopefully this was useful. I mean, there's a lot more struggling than my typical videos, but maybe it shows you a little bit of how I try to understand things. So yeah, I guess I'll see you in the next one.